Welcome to the class. Now topic of discussion is psychrometry and the associated tools like psychrometric charts. So here we are going to talk about mainly humid air or the air which has certain amount of water vapor. How to find out the properties of such a mixture or what are the critical conditions in this mixture. So we are going to see that. So in view of this, first is dry and atmospheric air. Basically, air is composed of N2 nitrogen, O2 oxygen and small amount of other gases. However, we also have small amount of water vapor in the air. Water vapor in the air. So, in general, air is treated as composition of dry air and water vapor. So basically the air is separated from the mixture, water vapor is separated. So air plus water vapor is treated as the air in general. So the air part of it is called as dry air. So air will be mixture of dry air plus water vapor. Now mass of water vapor is omega for unit mass of dry air. So we are going to see this, and we treat most of the times we treat water vapor as ideal gas, so that we can use its properties for calculations. And then by Dalton's law, we know total pressure of the mixture is equal to partial pressure of dry air plus partial pressure of water vapor. So this is mixture's total pressure. Now total pressure is equal to pressure of one component plus pressure of other component. So here we are having water vapor at partial pressure of PV. So now we are considering it as an ideal gas at that PV pressure. So we need to find out, suppose enthalpy, suppose H, which is function of H of T, then that can be found out as H, basically H nu of T for us is equal to Hg of T. So we practically mean that we will go into the vapor pressure, and that vapor pressure we will treat it as saturation pressure, and at that saturation pressure we will see in the steam table what is the saturation vapor enthalpy. So that is what we will make it as Hg, which is basically Hv at T. So at that temperature we would get that enthalpy. So we will get that. Then we will have some other terminologies which include specific humidity and specific humidity is what we are treating here is omega, and this omega is treated as mass of water vapor divided by mass of dry air. So it is ratio of mass of water vapor per unit mass of dry air. So this is an important terminology which is called as the specific humidity. We can make use of specific humidity to get an expression such that omega now is equal to mv divided by ma. We are treating both as ideal gases, so we have pv upon pv upon r vapor into T divided by P air into V. We are saying that water vapor and air both are in the same volume and they have same temperature. So volume and temperature would cancel. So we have omega is equal to PV upon RV divided by PA upon RA. So if we divide, if we take the standard values of RV and RA, we will get this number as 0.622 into PV upon PA, and then that we can denote as PV upon P minus PV. So this is the expression for specific humidity. Now there is one more term which is called as relative humidity, and this is denoted by phi. It is ratio of mass of air, mass of water vapor in the air divided by maximum possible mass of vapor in the same state. So phi is equal to mv and this is mg, which is saturation mass. We know that if we keep water in the air, it will evaporate. So water would get evaporated and the water vapor will mix with air. So in such case there is a possibility that air cannot accommodate the evaporated water. So the fact is there is a maximum possible mass which air can bear for the vapor. So beyond which air cannot accommodate the vapor. So such maximum mass is called as saturation mass of vapor, and then actual mass which is present for a given state of pressure and temperature. So this ratio is called as the relative humidity. So relative humidity is basically PV upon V divided by RT divided by, so this is mass of vapor. Now there is mass of saturated vapor which is Pg upon V divided by RT. So this is the mass of saturated vapor at the same, in the same volume and in the same temperature. So we have phi is equal to PV by, so here we are both having RV. So this would get cancelled. So we have PV upon PG, that means partial pressure of vapor at a given state divided by saturation pressure of vapor in the same state is the relative humidity. Now we can have expression for omega as 0.622 into PV divided by P minus PV. So we can make use of this expression and write down in terms of PV. So this will become P omega minus PV omega is equal to 0.662 PV. So P into omega is equal to PV divided by omega plus 0.662, and this gives us PV is equal to P into omega divided by omega plus 0.622. So this is, if we know specific humidity and mixture pressure, we can find out relative humidity. So we know that PV upon PG is equal to phi. So it is equal to P omega divided by omega plus 0.622 into Pg. So this is the formula for relative humidity in terms of specific humidity. We can also express in a different way. We know omega is equal to 0.622 PV upon P minus PV. We know that phi is equal to PV upon PG. So PV is equal to phi into PG. So omega is equal to 0.622 into phi into Pg divided by P minus phi Pg. So this is also an expression for omega if we know partial pressure of saturated vapor and also relative humidity. Relative humidity phi can vary from 0 to 1. This has variation between 0 to 1, where 0 is representing completely dry air and then 1 represent the fully saturated vapor or completely humid vapor. So after relative humidity of 1, we cannot accommodate any mass of vapor in the air. Now we know, if we want to find out the enthalpy of the mixture, then we can find out enthalpy of the mixture. Suppose total enthalpy of the mixture H is equal to enthalpy of air plus enthalpy of vapor. So this is equal to mass of air into enthalpy of air plus mass of vapor into enthalpy of vapor. Now if we divide everything by A, so this is enthalpy of mixture per unit mass of dry air. This is equal to HA plus omega into HV. So this is enthalpy of air per unit mass of dry air. So this unit will be kilojoule per kg of dry air. So now we will move towards next concept, which is called as dew point temperature. So we are talking about dew point temperature. Dew point temperature so if we have air at high temperature, then water evaporates and mass of vapor in air increases. If we decrease the temperature, of air, then vapor accommodation or bearing capacity of air decreases and air attains a saturation point beyond which if we decrease the air temperature, then vapor starts condensing. Since it has air has reached phi is equal to 1, and then since temperature is decreasing, we are having lower accommodation capability of vapor in the air. We actually are seeing in point 1 that if we heat the air, then basically temperature of the mixture increases, and since temperature of the mixture increases, we have more possibility of having vapor in the air, since air's vapor bearing capability would increase. Contrarily, when we are having lower temperature, then due to decrement in temperature, air's vapor bearing capability would decrease, and then if we keep on decreasing the temperature, then it existing vapor in the air would become the saturated amount of mass, and then onwards if we further decrease the temperature, then we will have condensation of water vapor. So the temperature at which water vapor would start condensing upon decrement of temperature of air is called as dew point temperature. So if we put it in a thermodynamic process, then we are saying that we are having water vapor at certain superheated state, okay, and then that is in the mixture of air plus water vapor, which we are calling it as air. So this is the condition. Now if we are reducing the temperature of mixture, obviously vapor temperature would also decrease, since vapor is in thermal equilibrium. So vapor temperature is decreasing, but we are doing it at the same pressure, so it is a constant pressure line. And then we reach a state where we reach the saturation vapor point of that pressure. So that saturation vapor point would give us the saturation temperature, which is called as dew point temperature. Okay, so dew point process is at constant pressure and we are attaining phi is equal to 1, which is leading to condensation. So the now next concept what we are trying to see is adiabatic saturation or wet bulb temperature. Basically phi and omega are very much required in design process. So what would happen is we need to estimate phi and omega. So estimates of phi and omega are required. So for that we need to measure few things and then we can estimate phi and omega. So for that we can make use of dew point, and there are also other procedures and other temperatures which are called as the wet bulb temperature or also denoted as WB. Actual temperature of the air, what would be measured using the thermometer is called as dry bulb temperature. So there is measurement for temperature of mixture using routine thermometer is called as dry bulb temperature, which is TDB. Now with these all measurements we can possibly estimate the specific humidity and relative humidity. The experiment for adiabatic saturation is this way, that we will have a long channel, and in this channel we would have filled water, and there will be air which is entering and leaving this channel. This channel is long enough for having saturation test to be reached. So we are treating it as 1, and this station is 2, and we are supplying some water if it is required from here, which is again at state 2. So here air is leaving, air is at temperature T1, omega 1, phi 1, and it will have vapor pressure PV. So it will go out with temperature T2, and then it will have specific humidity W omega 2 and relative humidity phi 2, but phi 2 is equal to 1, since this length is large, such that this water is evaporating in the air and it is getting accommodated in the air at every station, and air is having more and more water vapor getting accommodated in it, such that at the exit when air comes, it would have reached phi is equal to 1, which is the saturation state for the vapor. So if we try to write down the mathematical expression, then it becomes m dot A1. So for that container, if we redraw, then this is the container, and then this is the station 1, air is entering at T1 omega 1 phi 1, air is leaving at T2 omega 2 phi 2 is equal to 1, and then there is water supply of excess water or extra water or required water will be done from here, and then we have mass balance for air m dot A plus m dot A1 is equal to m dot A2. There is no change in mass of air is same, so we are saying that it is equal to m dot A, but there is change in mass of vapor, m dot omega 1 plus m dot F, and this m dot F is the makeup water which we have supplied from the bottom, since there was certain amount of water and that water got evaporated mixed with air. So we are supplying the makeup water from here. This is equal to m dot omega 2. So let us divide this expression by mass of air, such that we will have divide equation by m dot A. So we will have m dot omega 1 divided by m dot A plus m dot F divided by m dot A is equal to m dot omega 2 divided by m dot A. We know this is specific humidity at entrance, this is specific humidity at exit. M dot F into m dot A is equal to omega 2. So m dot F, how much amount of makeup mass of water is required? That is equal to m dot A, mass flow rate of air into omega 2 minus omega 1. So this much amount of makeup water is required. Now we can as well use the energy balance, and energy balance says that air with enthalpy H1 enters, and then it gets mixed with m dot F at HF2. This is the enthalpy of water corresponding to state 2 or temperature T2, and then it leaves with m dot A H2. Okay. So, this is the enthalpy of mixture per unit mass of air. This is the specific enthalpy of water at state 2 in the saturation state, and then this is the specific enthalpy of air at state 2, mixture at state 2 per unit mass flow of air. Then this becomes m dot A1, this becomes CpT1 plus omega 1 into Hg1 plus, we know now what is mf, and that mf is equal to m dot A into omega 2 minus omega 1 is equal to m dot A into Cpt2 plus omega 2 into Hg2. So, we can remove m dot A from all sides, and then we can put the expression in terms of omega 1 as this omega 1 here becomes equal to Cp into T2 minus T1 plus omega 2 into HFG2 divided by Tg1 minus Hg1 minus Hf1. Here Hfg2 is equal to Hg2 minus Hf2. What we are trying to do over here is basically, suppose we take this expression, then it is Cpt1 plus omega Hg1 plus omega 2 minus omega 1 into Hf1, Hf2 is equal to Cpt2 plus omega 2 Hg2. So, we can have Cpt1 on that side, and we will write down it with the all terms together for omega 1. So, omega 1 into Hg1 here minus Hf2 here, Hf2 here. This will be equal to Cp into T2 minus T1. So, we have accounted this and this plus omega 2 into Hg2 minus Hf2. So, this term is also accounted. So, this we can write down as Hg1 minus Hf2 is equal to Cp into T2 minus T1 plus omega 2. So, this is the latent enthalpy, which is Hfg at 2. So, we have omega 1 is equal to Cp into T2 minus T1 plus omega 2 Hfg2 divided by Hg minus Hf2. So, this is how we can estimate the omega 1, that is specific humidity at station 1, since we would have measured temperature T2 and T1, and then we would know the saturation enthalpy corresponding to T2 temperature. So, this gives us the expression for prediction of omega 1, or what we tell it as the specific humidity of the air. So, this temperature is also called as wet bulb temperature. So, in case of wet bulb temperature, a thermometer will be used. Instead of doing this experiment of dry saturation of the adiabatic saturation, we can as well put a wick of cotton on the thermometer bulb and then measure the temperature. So, in this process, the air and water, actually they will have heat transfer among them. For the latent heat, of the water for evaporation, and the temperature will reduce if we are having evaporation taking place. So, the temperature measured in such case by the thermometer is called as wet bulb temperature, which is almost same as the adiabatic saturation temperature. Now, we will solve some examples on this concept. So, here first example says that a 5 meter by 5 meter by 3 meter room contains air at 25 degrees Celsius and 100 kPa at relative humidity of 75%. Determine partial pressure of air, specific humidity, enthalpy per unit mass of dry air and mass of dry air and mass of water vapor. So, these things are to be evaluated. So, for these things let us make use of steam table for evaluation of these things. So, here we know that we are given with air temperature as 25 degrees Celsius, and it is the total pressure is given as 100 kPa and relative humidity phi is 0.75. We know that relative humidity phi is equal to PV divided by Pg. This is partial pressure of vapor and this is also partial pressure of vapor, but at the saturation state. So, we can go and see at 25 degrees Celsius what is the saturation pressure of vapor when we are having 25 degrees Celsius as the saturation temperature. So, for that we can find out Pg, phi is known. So, PV is equal to phi into Pg. So, and this is at 25 degree Celsius. So, PV becomes 0.75 into this pressure is actually here we are going to make use of the steam table where temperature is the part at the left hand side where we are going to identify the saturation temperature 25 degrees Celsius and go ahead. So, for 25 degrees Celsius pressure is 3.1698 kPa. So, this gives us 2.38 kPa as the vapor pressure. So, partial pressure of air is equal to 100 kPa minus 2.38 kPa, it is 97.62 kPa. Now, partial pressure of air is found out as it was asked. Now, we can find out specific humidity omega is equal to 0.622 into PV divided by P minus PV, which is basically PA. So, PV is known, PA is known, 0.662 is known, and then we get 0.0152 kg of vapor, which is H2O per kg of dry air. This is the unit of specific humidity. Now, we can find out the enthalpy of the mixture, which is enthalpy of air plus specific humidity into enthalpy of water vapor. So, this is enthalpy of mixture, or for us it is air per kg of dry air. So, having said this, we can find out HV, which is basically saturation enthalpy at 25 degrees Celsius, which is Hg at 25 degree Celsius, and then that we know it is 2546.5 kilojoule per kg. So, we have H is equal to Cp into T plus 2546.5 into omega, we just found out 0.0152, and this gives us H at 63.8 kilojoule per kg of dry air. So we found out enthalpy per unit mass of dry air. Now we have to find out mass of dry air and mass of water vapor. We can find out by using volume. So volume is 5 into 5 into 3, which is basically 75 meter cube. We know mass of air is equal to partial pressure of air into V divided by R into T. Here volume and temperature are same for the air and water vapor. So partial pressure of air is basically P minus PV into volume divided by RT. So we can get it as 85.61 kg. Here we are putting this T in Kelvin, okay, and here we are putting the T for air, and that T is in degree Celsius. So mass of vapor is equal to, in this case T is in degree Celsius, so Cp will have unit kilojoule per kg degree Celsius. So a mass of vapor is partial pressure of vapor into volume upon RT. So this will give mass of vapor as 1.30 kg. We could have also found out mass of vapor as specific humidity into mass of air as well. So this is how we would have solved this example. Now we will go in the next example, and this example says that dry and wet bulb temperatures are 25 and 15 degrees Celsius for 1 bar of air. So there is 1 bar of air, and then for that if we have measured temperature on just a simple thermometer, then it will give you 25 degrees Celsius. But if we put wick of cotton on the thermometer bulb and measure the temperature, then what will happen? Water will evaporate, it will take the latent heat from the existing water and some part from the air, and the temperature will decrease, and that decrement in temperature is measured, so that the temperature measurement shows 15 degree Celsius for 1 bar condition, and we are supposed to find out specific humidity, relative humidity and enthalpy of air. So we are given as dry bulb as 25 degree Celsius, wet bulb as 15 degree Celsius. We can make use of these two temperatures as the temperatures for formula what we have already derived. Omega 1 is Cp into T2 minus T1 plus omega 2 into HFG2 divided by Hg1 Hg2 minus HF2. Here we are knowing that this air would be saturated at 15 degrees Celsius. So for that omega 2 is 0.662 Pg divided by P2 minus Pg2. So under the assumption of saturated air, we can get for 15 degrees Celsius the saturation pressure we can find out, and then that pressure is 1.7057 kilo Pascal, and this is equal to 101.325 kilopascal minus 1.7057. So the saturation leads to the specific humidity of air for 15 degrees Celsius as 0.01065 kg of water per kg of dry air. Then this omega 2 will be used over here to find out omega 1. So omega 1 is equal to Cp, which is 1.005 for air. So this T2 is the temperature, which is basically Wb, and this T1 is basically dry bulb. Basically these are the temperatures at the inlet and at the outlet of the adiabatic saturation temperature measurement experiment. So here we are having this as T1 and this as T2. So plus omega 2 HFG2 divided by Hg2 minus HF2. Here we would find out HFG2 at 15 degree Celsius, the latent enthalpy at 15 degree Celsius. Omega 2 is evaluated. This we can find out from steam table. This is known T1, this is T2, this term is known, and then this term basically is Hg at, this is Hg1, this is Hg1, so this is Hg1, so this is Hg at 25 degree Celsius, which is liquid saturation, vapor saturation enthalpy at 25 degree Celsius. This can be found out from the steam table. This is liquid saturation enthalpy at 15 degree Celsius. So this would also be found out from the steam table. So we will open the steam table, we can find out HFG2, Hg1, HF2, and then find out omega 1, and this omega 1 is 0.00000653 kg of H2O per kg of dry air. We can make use of the relation phi 1 is equal to phi omega 1 into P divided by 0.662 plus omega 1 into Pg1, which is the saturation pressure corresponding to 25 degree Celsius. So these things will be known, and then phi is 0.332 or which is 33.2%. Now we can find out enthalpy of the mixture per unit mass of dry air as HA1 plus omega into Hg1. So here again Hg1 is the saturation enthalpy of vapor at 25 degrees Celsius. This is Cp into T. So Cp is specific heat is 1.005 kilojoule per kg degree Celsius. So we will know its degree Celsius as 25 degrees Celsius. So Cp into T. For the air is known, this is omega 1 is known, we have just now evaluated it as 0.00653. Hg can be found out from the steam table at 25 degrees Celsius vapor saturation enthalpy, and this gives us H as 41.8 kilojoule per kg of dry air. Now we have seen that how to analyze the humid air. Now we are going to see some more tools to estimate some more properties, and then we will go ahead with the understanding of condensers and cooling towers. Thank you.